Hi and welcome to this video. In this video, I'll be discussing the energy stored by capacitors. Do like and subscribe this channel so that you get to know when we are putting up the next videos, and also put down your comments in the comment box below so that I know which topics to cover next, as well as any doubts that you might be facing that I can help you with. So let's get started. Get your notebooks out, share this video with your friends so that all of you can discuss with clarity these subjects, which are very important to understand basic electrostatics as well as electronics. So let's get down to it. Okay, so first things first, we'll be starting with understanding how does energy get stored. Right, so let's make a capacitor like this. This is obviously a parallel plate capacitor, but the concepts apply for all forms of capacitors. Okay, so this is the minus side, that means this is negatively charged, this is positively charged. Now let's understand what we are talking about when we say that the energy is stored. Now the negative side of the capacitor, which is this side, obviously has a low potential. Okay, low potential, which means that this is at a lower level, and this, the positive side, is said to be at a higher potential. That means it is a little higher. Now think of this as a hill. Okay, think of this as a hill. This is plus Q and this is minus Q. Okay, this is a hill where I want to go and I want to take a charge dq, a small charge dq, from minus Q to plus Q. What's gonna happen? I will have to push, 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 so that eventually it reaches this point. Correct? Now in this case, when I am taking the example of a rock over a hill, it seems very simple that I have to push, but what's going to happen, all of that force, all of that energy that I exert on that stone, it gets stored in the stone as the form of potential energy. Right? It gets stored in the stone as the form of potential energy at this height. Right? It increases in this height. Similarly, over here as well, when I take dq, a small charge, from this end to this end, as I push it along, what am I pushing against? I am pushing against the electric force or the electric field that is existing within this capacitor. Right? So I am pushing against that electric field, I am pulling this slowly, 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 slowly till this point. And so all of this work to push this charge gets stored in that charge as potential energy of the charge. Right? It gets stored as potential energy. So that is what we are talking about. Now in this case, this was linear. That means if right now this is dq and next time I change it to d R, or next time I change it to ds, that means a small charge, the amount of work that I have to put is very similar every time. Right? It is similar. Why? Because at no point I am getting phased by the force. Right? It does not change really for me, but here the force changes. The force is not linear. The force is changing. As I'm getting closer and closer and closer to this side, the force on the charge keeps on increasing. It keeps on increasing. Right? Therefore, it is not as simple as that example, but the concept is the same. Okay? Just the way of figuring it out is different. So once we understand the concept that, hey, I want to pick up a charge from lower potential and take it to a higher potential, and all of that energy is going to store in it. So that's what I'm trying to do. Now in a capacitor of capacitance C, and we know the charge is Q. Let's take an intermediate. We are considering an intermediate stage. Intermediate stage means this side is not fully charged and we are trying to charge it slowly. So how are we charging it? Let's say that at the intermediate stage the charges are Q dash. Okay, the charges is Q dash. So if I write V, which is the potential is equals to Q upon C. C is fixed because this is the capacitance of the capacitor, but this is Q dash. Why? Because we are taking the intermediate stage where this the capacitor hasn't fully charged. So Q dash is the charge yet, and the potential is also V dash. Why? Because the potential is also not fully there. It is still in the intermediate stage. So this is my intermediate stage potential. Now potential is what? Potential is the work done or the potential energy of a unit charge. So when I am pushing dq charge, how much will be the potential energy? V dash into dq. Okay, I am using capital Q this time so that it's easier for us to understand, but I am using this will be the potential energy of the charge, right? Makes sense? So that's why we are taking dq, and I will have to multiply the same on the other side as well. So Q dash upon C into dq. Now this is also the work done in this intermediate stage. So I'm saying, let's call it dW. This is the work done in the intermediate stage on a small charge dq at this particular point. So this is the delta W or dW at this stage. So if I want the full work done, the total work done through and through, as well as the total potential energy, what will I do? I will have to integrate. How will I integrate it? I will integrate it from 0 to Q. Why? Because I am starting from 0. I want to charge this point till Q. So integrating it this way, I will have Q dash upon C into dq. Now I can clearly see a definite integration happening over here. I can solve it very easily and simply. When I solve it, I get W over here, W at Q minus W at 0. W at 0, or the work done at 0, is obviously 0, so I am not writing it. So this is 0. Okay, sorry, my bad. This will be D. This will be W. So W is equals to 1 upon C and 1 upon C into, now Q dash, integration of Q dash dq will be essentially Q square upon 2 to the limit 0 to Q, which will give me 1 upon C Q square upon 2. Okay, so this gives me my W, or the total work done, as equals to Q square by 2C. And this is a very important result. Okay, it's a very important result in this case, which is the energy stored in a capacitor. So this is my total work done on a charge in a capacitor. Okay, so W equals to Q square upon 2C. Now I can write it in different forms as well. Such as work done is equals to Q square upon 2C, as well as I can write Q upon C as V, right? So Q upon C becomes V. So I write half Q into V, right? And sorry, this becomes, yes, Q upon C is V. Then we can also write it as half Q upon I divided by C square, so I get C into V square. Okay, so I multiply C both below and above, so I get half C into V square as well. Okay, again an important one, and so on. So these are all the different forms of work done or writing the result, the same result in different forms. Now again, from the same thing, this is the total work done. Now what are we working against? We are working against the electric field of the capacitor. So this energy, this potential energy, is getting stored where? It is getting stored in the electric field in between this capacitor. Okay, it is getting stored in the electric field in between this capacitor. How do we find that out, and what is the value? Let U square upon 2C is equals to, I will write it in the sigma form. What is sigma? Sigma into A is equals to Q. Why? Because sigma is surface charge density, that is the charge on unit surface area. So when I multiply it with the total area of the plate, I get the Q, or the total charge. So now I'm going to write it in that form. So Q becomes sigma square into A square upon 2C, and I'm going to write C, that is, for a parallel plate capacitor, the capacitance is essentially epsilon naught into A upon D. So I'm writing it in this way. Now I can see that okay, so another thing, because we are trying to find that how much energy is stored in electric field, so obviously I need to get it in the form of electric field, and electric field is essentially equal to, electric field for a parallel plate conductor is essentially sigma upon epsilon naught. So I'm gonna use that here. How am I gonna use that here? I'm gonna multiply this with epsilon naught on top and bottom. I will get half sigma square upon epsilon naught square into epsilon naught A into D. Okay, so I get, this becomes E half epsilon naught into E square into A into D. Now what is A into D? A into D is essentially the volume, the entire volume of this capacitor. So what if I divide this by A into D, or the volume? What do I get? Remember, this is the total energy stored. This is the total energy stored because we were looking at the work done against the electric field. So this was the total energy stored in the capacitor. Therefore, energy stored per unit volume is now equals to half epsilon naught E square, right? Because we divided by the volume. So this is how much energy is stored per unit volume of the capacitor due to the work that we are doing, right? So that is it in this video. If you liked it, do like, subscribe and share this video, as well as put that notification bell on so that you get to know when we are putting up the next videos up, right? Put down your doubts in the comment box below so that we know what doubts you have and what suggestions you have for the next videos I should be making. Thank you, and I'll see you in the next video.